Hang on.
Okay. And just to remind you all that this is being recorded, so anyone that you know that missed this meeting can go into our website and pull it up. Or if you want to watch it again, you can go into our website. Give us a day to get it loaded in there. But that's why we're recording it. I'm your president, Gordon Rosner. And let me explain, if you are seeing the panelists' thumbnails, the faces of the panelists, those who are given the presentations, and you don't want that, it might be hiding some of your screen, is there will be a button that, I might even say more, but it's hide video panel. You can click on that and then you would have a full unobstructed view. And then if you want to see the video panel again, you can just go on down and it says view video panel. So sometimes that helps. And in fact, I'm going to get out of there and welcome. Live long and prosper, everyone. And I hope everybody lives long. And by prospering, I mean to share in our meetings and our presentations. So hope you live long and prosper by being a part of our meetings. I will back up just, let's see. Yeah, a little frozen up here right now. Yep, having some technical difficulties here. Okay, so some of you may want to have a pencil and paper handy because we'll be talking about some websites and some cool stuff. And so you might want to write it down, or what you could do is take a screenshot also of some things that are interesting to you. So yeah, pick up a pencil and a paper and get ready to write some stuff down. So introductions, I do this all the time just to remind people that this is your leadership team that's working all the time to make sure that the club functions properly and continues to function, gets our presenters lined on up, pays the bill, suggestions, do some voting. So they're always in that background keeping our club going. But look at the lower left corner there. The most important member of the club is you, right? Without you, these guys would have nothing to do. So let's keep them busy. And our next EVAC meeting is Friday, the 19th of March. And the main presentation will be a far-side array. By that, far-side meaning the far side of the moon. Far-side array for radio science investigations of the dark ages and exoplanets. Wow, that's something new. So we'll find out all about it come next month. And remember, this is the last time I'm going to put this slide on up, but dues are due. So for the year 2021, you keep the club running. If you are a member, please consider renewing your membership. If you're not a member, then think about joining our club, because we do plan on continuing these Zoom meetings for quite a while, for sure. Down at the lower left, you can see that they can be paid online via the club website, or you can mail the application too. You can fill it out by hand and mail it on in to the club's address, which again is at the bottom of our website, main page of our website. So the club news, also the club olds, right? So as usual, all EVAC personal contact events still remain canceled. That's everything. Everything that we used to get together on is still canceled. We don't know when it's going to come back. Safety considerations determine that. But we sure are hoping that sometime later this year we can start opening up again. But that's a hope at this time. Member presentations. Remember that anyone that wants to give a member presentation about anything that astronomy subject is, let me know. And just shoot me an email there. You can do it via our website, the EVAC president link. And yeah, we'll get you on board. Member articles. Now this is something new. This is something we opened up. If anyone wants to write an article, maybe you started astrophotography and you want to tell everybody about your successes and failures. And be prepared, because if you're starting astrophotography, you're going to have a lot of failures. But the successes are sure worth the failures. Things like that, or anything. Maybe you visited some place or will in the future, and you wanted to let people know, like you went up to Lowell, or you went down to Tucson, and write up a little article about how it was. So again, just let me know by that link that you have a member article, and you can submit it, and it would be included in our monthly newsletter. So think about that. We're part of a club. Everything that people do in our club, astronomy related, is going to be interesting to other members. And remember, these monthly meetings are recorded so that if anyone misses it, they can go into our website and they can pull it on up. The International Dark Sky Week, that's not until April, but I thought I would add it here now, is the International Dark Sky Association is putting on a International Dark Sky Week, April 5th through the 12th. And if you want to learn more about it, there's a link down there. Click on that. You have to sign up for it so that you'll get other links. You'll get a schedule of what's going on. And you know, this organization is down in Tucson. They're worldwide, but their push is to get the public knowledgeable about the lights, the lighting, and how it ruins the night sky, and what everybody can do about that. So think about looking at that. I certainly will be. All right, introduction to amateur astronomy, the Kalamazoo Astronomical Society. Hopefully, a lot of you have been watching this. It is fantastic. Now it says introduction to amateur astronomy, but it is applicable to everyone. Seasoned veteran, it's a good review of the basics. The way it's presented is fantastic. Richard Belle, the president of the club, does an outstanding job. It's offered basically every other week, 5-week course. The first one was on one place among the infinities, where he just talked about various objects up there in the night sky. And then the second one was discovering the night sky. You know, how do we do that? How to work a planisphere, the constellations, how to star hop. It was things like that. And now tomorrow is the third presentation, February 20th, binocular basics. So anyone who's starting out with astronomy, they say, you know, what type of telescope should I get? Well, we recommend that if you've never done this before, how about investing in some good binoculars? Because no matter how far along you are, binoculars are always a valuable tool. I mean, I've been out at this since I was 14 years old, and I still find myself going out in the backyard with my binoculars and just grazing the sky. There's always something to see with binoculars. Then the next one is going to be telescope tutorial. Hey, what telescopes do I buy? What's out there? What's the price ranges? How do they work? What's best for me? They're a tool. And I know anyone who is starting to get into astronomy, who wants to get in a telescope, is overwhelmed by all the different types of telescopes out there. So this would be an excellent one to take a look at. And then they'll wrap it up with the art of astrophotography. So they'll roll everything together and talk about how do we get started in it? You know, what type of camera? There has been such a revolution and explosion in astrophotography lately that it's getting less and less expensive and more push button type stuff, although that push button can take a long time. But yeah, definitely, if you're interested in astrophotography, sit in on the March meeting. Now down at the bottom, you have to sign up for this. And there's their registration link, KAS Online. That's Kalamazoo Astronomical Society. They're linked down there. I also have Eastern Standard Time circled because 1 to 3 p.m. is Eastern Standard Time. So in Arizona, it's 11. And then, of course, any of our friends around the country, around the world who are listening in, they'll have to figure that out. So remember, it's Eastern Standard Time. So please join in. If you have the slightest inkling, check it out. It's well worth the 2 hours. And they do things like, I took a screenshot of this, a handy tool to determine the degree spread as you hold out your arm. And the 10-degree one is the one that we're most familiar with. But look, there's 1 degree, 5 degree, your hand is a very handy tool. And if raising your arm seems too much of an exercise, well, you can use the Big Dipper. And that one down at the bottom of the bucket just happens to be a very nice 10 degrees. And that's the one that basically I use because I can't really remember the other ones. But that bottom of the Big Dipper, 10 degrees, and then you can extrapolate from there on the night sky. So congratulations, NASA. Right? Yeah, Perseverance yesterday landed on Mars successfully. Yay, NASA. I was watching it all morning and continued all afternoon, and what a great job. What fantastic for humankind. Now the rover Perseverance looks very, very similar to the last one we sent on up there, Curiosity. But it is totally different. Lots of more instruments on there. There's 23 different cameras on board. Of course, the technology is a lot better now. And its prime mission is to search for evidence of life. So it's going to be drilling holes and roaming around, taking all different pictures in that. So congratulations, NASA. What a great job. And looks like it's cold up there from the first picture that was sent back. Our little friend there. So our member presentation will be by Bruce Barron. Now, Bruce was the program manager for guidance, navigation, and control at Orbital Sciences. So his presentation is going to be on simple orbital simulation. He spent 10 years at McDonnell Douglas Helicopter, managing the Apache helicopter guidance, navigation, and control group. He worked at Sperry on aircraft and spacecraft control systems. He worked on autopilots for the DC-8, DC-10, F-22s, F-17s. The list goes on and on and on. And this is an example of a club member who says, hey, I've got some things here. I got some experience that I think people would enjoy seeing, and great timing because of all the launches that are happening these days, and especially the news about Perseverance, is how is all of this done? How are the orbits calculated and how are they simulated, right? So Bruce, I'll introduce Bruce Barron to you, and Bruce, you can take it over.
Okay, I'm going to go to share screen.
Yep. So I've stopped sharing.
Okay, does everybody have that?
Yes, I can see it quite well.
Got a picture of the V2?
Yes.
Okay. What came about, actually, having a discussion with people on the utility of computer games. And we talked about one of the first computer games called Space War, written in roughly 1961, and pointed out that if NASA had played that, they would have done a lot better on the Gemini 4 mission. And wanted to show exactly what the situation was with Gemini 4. And this is the case. This is the first attempt to dock in space. And the Gemini went up, 2 astronauts on it, and they tried to dock with a second stage of a rocket that had been launched earlier. And it didn't go quite as they had expected. The the person I was discussing this with did not have a technical background, so I tried to do a simulation using no calculus, no trigonometry, and as little algebra and other physics as I get by with. So it's a very simple simulation. What I'm going to be showing you later is actual simulations running on my computer at the time. So one of the advantages of Zoom is you can link to my computer and actually show you what's going on here. Okay, the basic way it works, it's a discrete simulation, which means I only look at the parameters at fixed intervals of time. Typically use 1 second or 1 millisecond, but for this simulation, I'm looking what happens to the spacecraft at every 1 minute interval. Those of you not familiar with vectors, it's a value that has a sign and a direction, and something in one axis cannot affect the other axis. I'm using Newton's law that acceleration equals force divided by mass. And I've got justifications for these simulations if somebody wants to get into them later. The assumptions I'm making here is the Earth is homogeneous. That means there's no gravity anomalies in it. The center of gravity is always at the center of the Earth. I'm assuming the spacecraft is going to orbit the center of the Earth rather than the center of mass of the entire system. Considering how light a spacecraft is, the difference is 1 part in 10 to the 18th. That's 10 with 18 zeros after it. When I get to the Gemini situation, I'm assuming the force between the two spacecraft is 0. It's actually in the micro or nano newtons, so it's really very small. I'm assuming spacecraft are in the same plane. If they weren't, when they try to dock, they'd have a cross-axis velocity, which would result in a huge explosion. So we assume we're in the same plane. Now, I'm not making any assumptions at all to start with on the shape of an orbit. I mean, we all know it's going to be circular or actually elliptical, but I'm not making that assumption. That's just going to come out of the simulation by itself. The only thing I'm using in the simulation is force of gravity, and acceleration is force divided by mass. So it's a very simple simulation. I'm working in units of meters, kilograms, and minutes. I'm assuming the Earth is using the mean radius of the Earth as opposed to the polar diameter or the equatorial diameter radii. So the way this simulation works is we define an initial condition. I start off with a spacecraft in orbit or in the air, up high, and give it an initial position at a given velocity. I then calculate how far it is from the center of the Earth. From that, I determine the gravitational force. And then once a minute rather, I take the acceleration I got from that force and use it to update the velocity information for the next iteration. I use the old velocity information to update the position information for the next iteration, and plot this on a graph. The programs themselves are written in MATLAB by MathWorks. This is used by many millions of engineers and scientists around the world. For commercial use, it's very expensive. For home use, it's not too bad. But there's a free version of a program called GNU Octave, so it's available to download for free, and it will work. It will run these programs with no problem. If you haven't used it and are interested, you can use the tutorials on the MathWorks site to learn how to use Octave, since it does work with MATLAB. And like I said, the programs are available if anybody wants them. Just contact me at the email given at the front end of this, and I'll send them to you. They're about 100 lines each. Other shortcut I'm taking, I'm using a rectangular integration rather than a trapezoidal or a much faster Runge-Kutta. The difference in the simulations is less than 10%. It's actually less than 1%, and they execute much, much faster for this kind of software I'm using. So first I wanted to verify the software. So all I did was start with the spacecraft in orbit, start with the spacecraft in the air or up in space, and give it an initial velocity and position, and let it fly for 5 orbits to see if it does look like a circular orbit. These are updates once a minute. I'll get into simulation in a second. This I thought was kind of interesting picture. A couple years ago, my wife and I went on a cruise of Australia and New Zealand. And while we're cruising past New Zealand, we saw a rocket ready to launch a satellite. It's an American rocket being launched from South Island in New Zealand. And they actually had to scrub the launch because our cruise ship didn't get out of the way in time. Now let's see if this will work. Takes a second for the MATLAB software to load up. Okay. I was going to plot that's the Earth, and this up here is the spacecraft, and it's just start off with a given velocity, and that's just free falling. And as you can see,
Hey, Bruce,
yeah,
it looks like your presentation is showing and not the MATLAB simulation.
You might
okay.
have to share your whole screen or stop sharing the PowerPoint and share the simulation only.
Let me shrink this down. Let's try this. You have it now?
There we go.
Okay, let me run it again. So you see the spacecraft's flying around the Earth, pretty much a fixed distance above it in a fairly circular type orbit. This was just to check the basic simulation works. Next, I'm going to try a Holman trajectory. This is a low energy trajectory used to transfer from one orbit to another orbit. Again, I'm assuming there's only two bodies, just the Earth and the spacecraft that we're in. A Holman is an orbit, is an elliptical orbit that's tangent to the original orbit you're in and the final orbit you want to wind up in. To change orbits, you give it an initial one-time burn to go from the circular to elliptical. And then when you hit the apogee of that ellipse, you give it another burn, and that'll circularize it in the new position. The amount of delta V you have to give, I just took the equations out of Wikipedia. So I'm going to fly 2.5 orbits at roughly 500 kilometers above the surface. Then I'm going to hit it with a one-time burn of less than a minute. And then I'll fly 2.5 orbits in an ellipse. And then after those 2.5 orbits, I'm going to apply a second burn. And this will circularize the orbit from the elliptical to the new circular orbit at an altitude of roughly 2,000 kilometers above the surface of the Earth. Let's see if this one works better. Worked faster last time. Do you have the simulation or the MATLAB screen up there? Here's the simulation. You have that?
Yeah, we see it.
Okay. So first it's flying the same orbit it flew last time. It's actually updating once a minute. This is a 90-minute orbit. So the graphic is only being updated like every 10-minute equivalent or so. At this point here is where I kicked it. Increase the velocity one time, just a sudden impulse burn. And you see it's lengthened out the orbit. It's elliptical now. Perigee, the closest point to the Earth, is about the same as it was, but the furthest point, the apogee, is significantly further. It's 2,000 kilometers away from the surface rather than 500 where I was. And there I gave it another kick right there. Both of these are increasing velocity. And again, everything other than the 2 points where I accelerated, everything's just free fall. And you can see it's now free falling in another circular orbit, but this time at significantly higher altitude or further distance from the center of the Earth. Where'd Zoom go? There. Okay, now I'll get to the Gemini 4 issue. So there's the first attempt to dock, was also the first spacewalk. And when the Gemini capsule got into orbit, it was behind the target. So they wanted to catch up to it. So naturally, they did what seemed intuitive, is they went faster. And it turned out the faster they went, the further behind they got. In this case, in the previous 2 simulations, I used actual altitudes and velocities. In this time, I changed them a little bit to accentuate the issue. And I'm starting initially with the Gemini about 20 degrees behind the Titan target. Normally, it would, it would be a lot closer, just in a single or a few kilometers, just type distances. And the one-time acceleration I'm using to try and catch the target is 1% of the existing spacecraft velocity. I'm not sure how much they actually use. 1% is easily within the capability of a spacecraft or satellite. I don't have the Earth on this one, but here's the Gemini and here's the Titan that's trying to catch up to. I'm not doing anything yet. Just following around orbit like they did in real life, doing housekeeping functions and planning the mission. And there I accelerated. And you see the acceleration puts me into an ellipse similar to the Holman orbit. And the ellipse is further, the apogee is further from the Earth than it was, which means while its linear velocity is faster, the angular velocity is slower. It's taking longer to go around the orbit. So each pass, it's getting further behind the target, even though it's going faster than it was before. Go another 1 or 2 times, you can see the distance between the the plus and the circle are further apart. Because the increase again boosted the orbit up, made the orbit longer, which means it takes longer to fly around it. It'll end in a second. Then I'll show you what happened, what they should have done and wound up doing on future missions. Over here is a curve of the distance between the two. So as it, these minimums here are when they're, close together, right in this area, and the peaks, these peaks here, when it's over this area here. But you can see it just keeps growing and growing as it's getting further behind it.
typo there.
I learn how to spell. Maybe. I had this set up to make it easy. Oh. This time I slowed down 1% instead of speeding up 1%. Okay, now I slow down. When I slow down, it puts me in an elliptical orbit. This time it cuts inside the original orbit, which means it's giving me, I'm going slower, but it's a shorter path, so it's taking less time to do one orbit. You see it's catching up and catching up. I guess it's already passed it. All right. As soon as this finishes here. Remember the red lines start off behind the, this guy here, the circles start off behind the plus sign. Now this should be the last pass. Come on. I'll stop in a second if it doesn't finish. Okay, this time, here it's flying the constant distance behind. Here's where it slowed down. And you can see the slowing down actually brought them into contact. And then we start running ahead of it with similar type curve that we had before. So like I said, it's counterintuitive, but that's the way things work when you're in free fall. And it turns out the original computer game called Space Wars, which was developed at MIT, was actually two spacecraft in orbit flying after each other and shooting at each other. And we saw it on that. I first saw it in '63 that you had to work backwards to get the targets to coincide. So that's the rest of this is just the justifications for the shortcuts I took. So that's about all I wanted to show.
Hey, all right. Okay, Bruce, thank you.
Welcome.
Thank you. Now, yeah, not very many people know about this. Gemini 4 had a problem. You know, intuitively, the pilot said, I've got to catch up with my other spacecraft, gave it more power, and by gosh, he got further away. So that's the difference between flying in the atmosphere and flying in orbit. So thanks, Bruce, for explaining that. I think everybody got that idea. So Tom, I will hand it over to you for our main presentation.
All right, thank you, Gordon.
Sure.
So Bruce, in the Q&A, there's a couple of questions for you. So you might want to take a look at that and see if you can give them an answer. But yeah, right now it's my pleasure to introduce our featured speaker, Dr. Belle. He's been on the Lowell faculty since 2011 and is a noted world leader in astrophysical research and remote sensing utilizing telescope arrays. His research concentrates on the fundamental property of stars, masses, linear radii, and temperatures, which tell us about the internal structure and evolution of stars. And he's also applied his interest in the highest resolution, highest precision astronomical techniques to detect such planets and map the surface of stars. And Dr. Van Belle's pioneering stellar surface imaging work at PTI won him the inaugural Edward Stone Research Award at NASA's JPL in 2001 for the first ever direct detection of stellar oblateness on rapidly rotating stars. And recently he served as the director of the Navy Precision Optical Interferometer, NPOI, remember that, in Flagstaff, Arizona from 2017 to 2018, and is now the chief scientist of NPOI. And NPOI, perhaps Dr. Belle will tell us more about that coming up, but it's a advanced telescope array at Lowell's Anderson Mesa Dark Sky site, roughly 10 miles outside of Flagstaff. NPOI links multiple optical telescopes spread over a site many football fields in size to form a single larger synthetic telescope. It is the largest such operational facility in the world with potential telescope separations of up to 430-ish meters and the only one expressly built for the challenge of visible light operations. And as chief scientist, he will implement revolutionary new advances in optics and electronics at NPOI. And to top that off, Dr. Van Belle has worked on every major optical interferometer on the planet Earth, including the Infrared Optical Telescope Array, the Palomar Testbed Interferometer, the Chara Array, the Very Large Telescope Interferometer, and the Keck Interferometer. So at this point, normally we'd give you a warm audible applause welcome, and please take it away.
There we go. Thank you, Tom. I appreciate that. Let's dive right in here and see if we can get this going. Everything look good? Thumbs up?
Looks great.
Very good. Yeah, so I'm going to talk a bit about Lowell during the pandemic. So basically our past year of what we've been up to and working on some things here. We've kept ourselves busy, basically, is the short answer. We have had quite a few things going on, and there has been a big downturn in our visitation to Mars Hill because our public program has effectively been closed. We've had some kind of cracks in the door opening things up, but the research programs and the other things that are usually happening behind the scenes have continued to happen behind the scenes. So let's go through a few of the things that have been near and dear to my heart. We've been working on continuing to work on this interferometer that Tom was talking about during the introduction. So let me give you an overview of that. The Navy Precision Optical Interferometer is an interferometer that is about 10 miles outside the city center of Flagstaff. It's on the Anderson Mesa site for Lowell, and it's big. We have 3 arms that reach in this Y shape, so big that you can easily see it on a Google Maps view. And along these arms, we have spots to park telescopes and feed light into the system. One of the things that, as you know, the atmosphere does to light is it makes the stars twinkle and gives you all kinds of problems. And so we try to not add to our woes. So one of the things we do after we collect the light is it immediately gets piped into through a window into a evacuated pipe, a vacuum system. And all the light goes from these arms to the center of the array. And then we relay it from the center of the array through this little stub arm to a laboratory where we blend the beams back together. And we're built so that we can take up to 6 telescopes at a time and join them together. This is a partnership between Lowell, the Naval Research Lab, and the U.S. Naval Observatory. And we each get portions of the observing time on NPOI. And it's been actually in operation for about 25 years. But we've been embarking on a very big upgrade at the site over the past few years. We've been trying to incorporate into the site 3 1-meter telescopes. Let's take a look at some of this. This is what it currently looks like as far as the feeds that do take light off the sky and relay it into the pipes. We call this a siderostat flat. They actually literally are just flat optics that track the sky and send the light off of other flat optics all the way to the back end. And the effective aperture of each one of these is about 12 centimeters. That's about 5 inches. And we have 6 of them that are built just for imaging. We have 4 more that are kind of specially built, a bit more instrumentation on the back end behind them for doing astrometric work on the sky, for determining the positions of stars on the sky. We can select 6 of these overall 10 apertures to synthesize our bigger telescope. One of the things that happens is when the light gets relayed to the back end, it has to have traveled, for each input aperture, it has to have traveled the exact same distance to within a fraction of a wavelength of light. And so we actually have inside of our system, when these vacuum pipes get to the back end, we relay the light into more vacuum pipes, and inside of those we have literally little trolleys that run up and down rails with mirrors on the trolleys, and we can thereby for each of the 6 beams vary the distance that it travels along that trolley, and those trolleys help equalize the distance from the star to the siderostat to the trolley back to the camera. And then the camera, the beam combiner, is where the light gets blended back together, and we can thereby synthesize a bigger telescope. If you think about it, this is a very clever thing. If you think about it, your refracting telescope or your reflecting telescope, when you draw rays of light through it and you bounce off the primary and you bounce off the secondary and you get to your imager in the back end, if it's a diffraction limited system, any ray of light that you can draw from an object in the sky that's in your field of view satisfies this equal path length condition. That's how interference works. And so every optical system that is diffraction limited is actually satisfying that sort of condition. And so we just do it dynamically rather than with a fixed static system like most telescopes typically do. So the problem is that those 5-inch apertures are quite small. And so we received a grant from our partner, from our Naval Research Lab partner, to start off with getting 3 of these plane wave telescopes from Planewave, which is now totally located in Michigan. When we started doing business with them, they were basically half in Michigan and half in the Los Angeles area. And the low cost of these telescopes relative to what up until that time had been the standard cost for a 1-meter telescope, they really hacked that down and made it possible for us to embark on this project. They've actually even lowered the price further since then. But we're happy with what we have. We have 3 of these telescopes that are starting to be used individually out at the site, and we're soon going to loop them into the array for use in concert. And we basically get between about a factor of 50 and 100 increase in collecting area. And so we'll be able to go from our current limiting magnitude, which is about 5th magnitude. So basically anything you can walk outside and see with your own 2 eyes is basically what we can do with NPOI right now. And we'll be able to blow past that goal all the way down to about 9th magnitude, which is actually a big deal for us. That means that we can really get to some very interesting things, both scientifically. The Naval Research Lab is interested in using this for looking at geosats. That's a hard problem to do, is to make resolved observations of satellites that are very high up. And so we're working together with common purpose in that regard. The thing about the array is that you can pack your telescopes close together, or you can actually spread them really far apart. it's basically like changing the zoom on your lens if you have a zoom lens camera. And so we want to be able to have very, very short baselines, on the order of 10 meters. And we also want to use the full extent of these arms, each of the 250-meter arms from, if you map it out from tip to tip of these 250-meter arms, it's about 432 meters, about 4 football fields across. And we want to be able to move things around. So we came up with this idea of basically putting a standard Astrohaven dome on a trailer, and inside of it we have a spot where we can look at the telescope, and that actually that pedestal that you can see there, it actually can be lifted hydraulically and then locked into position, and we can drive it around, and then we can gently lower this back down. And so this is kind of a Rube Goldberg idea, except we actually went ahead and did it. So our first telescope showed up in 2018. The plane wave guys are just great. They show up, and within about 6 hours, the whole thing's put together inside your dome and on sky, getting fully aligned images. It's really, really hot stuff. We have these domes that were provided by Astrohaven. Astrohaven actually provided the domes and the trailer. They did the whole kit for us, which was very nice of them. And this past summer, we did our first big move where we hitched this up to our Bobcat and basically pulled our ET, our enclosure transporter, number 1 and number 2, from the assembly spots to the center of the array for their initial testing. So you can see us moving it around, and then when it finally arrives here at array center, you can see ET2 getting ready to pass ET1, and we park them right next to each other. And so our next steps are going to be to get them to be used together with each other. Right now, actually, ET1 is observing as we speak right now as a regular single telescope, and doing some asteroid light curves. I was talking about that before the festivities began. We're also out there at the NPOI site. We're putting together a next generation beam combiner. All the magic is actually inside of this thermal enclosure here with the blue top. We do some fancy stuff with this. We're incorporating some new technologies where we take the light, and the light that has come to the back end through these vacuum pipes and through these trolleys, and once it arrives at this instrument, this vision instrument, everything's in lockstep. The path that each of the 6 beams has traveled is the same to about 10 nanometers. That's our positioning accuracy in piston for those trolleys in the on the fast delay lines. And what we do with vision is we put the light into fibers, and we can then line the fibers up because of these integrated optics, and take pictures with that. And so the way that works is the fibers, if you take light and you want to interfere it with other bits of light, but it's in a fiber, you got to be very careful, because you still have to preserve all the properties of the light. So the fibers have to be single mode, polarization maintaining fibers. What single mode means is that the diameter of the core of the fiber is about a wavelength of light in diameter. It's about a micron in diameter. So that means light can travel through that in only one way. A more common sort of fiber you'll see in telecommunications and most telecommunications applications is multi-mode fiber, where the core is not a micron across, it's more like 100 microns across. And the upshot of that is light could go straight through the fiber, or you can kind of have it skip from wall to wall to wall as it goes through there. There are many different modes that the light can travel. And so if you do that, its path length, the distance it travels through the fiber, changes depending on if you go straight through or kind of have these glancing bows through the fiber. And so then it won't interfere with its companions, because you'll have all sorts of different distances through the fiber. And then you also have to have it so that the electric field vectors line up. And so you need polarization maintaining fiber. These integrated optics is basically taking the technology that's been built up over the last few decades that goes into now building computer chips. And we're now starting to apply that to actually etch photonic devices into substrates. And so you can actually put light. Once you get into a fiber, you can then stack these fibers inside these integrated optics, and you can have these things blend beams together or split beams apart. You can have them route beams around. You can have these things act as special devices that have polarization effects, quarter wave plates, half wave plates. You can basically etch all that into fibers, put a whole optical table onto a chip. And for vision, our integrated optic is about the size of your pinky fingernail. And then the last thing that's really cool about this new vision instrument is that we have electron multiplying CCDs. And these are basically CCDs like you have on your telescope at home, but they have a special electron multiplying bit of circuitry that acts as a amplifying effect. It's a lot like the same kind of principle that you have with the avalanche photodiode, where you have a photoelectron that basically goes through the amplifier and it gives off a spray of more electrons, which makes more electrons, and so on and so forth. So you get an amplified signal coming out the back end, and you're able to really increase the sensitivity of these CCDs. The last thing we need to do to really route those 1 meter telescopes into the back end so that they can be sampled by this new vision instrument is the telescopes are so big that we now have to worry about the corruption of the atmosphere across the face of each mirror. So we need to have adaptive optics on each one of these. And so each one of our 1 meter plane wave telescopes, we've taken over one side of the yoke, and we've put a big old breadboard on the side. This is about 42 by 48 inches in size. And we're mounting onto that breadboard all kinds of optomechanics, which will help us flatten the wavefront. There is, gosh, where to go? There's an element, I think it's this one right here, which is one of these mirrors that has about 40 electro actuators on the backside of a very, very thin reflective layer. And you can piston each one of those independently and reshape that mirror so that it mimics in opposite what the corruption of the atmosphere has done to your wavefront. And then you get a nice flat wavefront out the front. You get a nice diffraction limited image. So once we've done that and we send the light into the pipes, we should be able to get our first interference fringes with a pair of these 1 meter telescopes, and then hopefully soon thereafter 3 of those telescopes at one time. And then we'll also are going to be adding a near infrared camera to do this not just in the visible but in the near IR. So we're keeping ourselves busy with NPOI. I'm not the sort of person to sit very still, and so I've been working on some other hardware projects as well that I wanted to highlight. In fact, this one's kind of near to me right now. Literally, it's about 2 stories above me right now. I'm currently at the Lowell Observatory Discovery Telescope. It's a 4.3 meter telescope that we have on Happy Jack, about an hour outside town. And we have a suite of instruments on the back end. This is what the 4.3 meter telescope looks like. You can see a couple people here next to it for scale. And it's a very interesting facility in the sense that on the back end, we have a instrument cube where the one face of the cube mounts to the telescope, but then the other 5 faces of the instrument cube can each have an instrument put on. And so one of the things that we've been playing around with is speckle imaging. And so what speckle imaging is if on a big telescope like this, if you look at an object, let's say a star, and you highly magnify what you're looking at, you'll basically see a lot of distortion because the full resolving power of the telescope is usually corrupted by the atmosphere. The atmosphere limits you to roughly about an arc second of resolution, spatial resolution on the sky. But if the atmosphere wasn't there, you should be able to get down to the true diffraction limit, which in the visible with a 4.3 meter telescope is about 40 milliarc seconds. And so what we do with speckles, we try to basically game the system and get past that. So let me show you what that looks like. So we've started off, we had a speckle camera called Dizzy, the differential speckle survey instrument. It had 2, again, of these electron multiplying CCDs, 2 of these EMCCDs, and we sent the R band light over here at about 600 microns, and then we sent the I band light over here at about 800 microns. And it was a very successful instrument in what it did, and you can tell that because this instrument's very compact. It visited a lot of telescopes. It was kind of a traveling instrument. And every place that it went, both here at Lowell, the Wind Telescope down at Kitt Peak, it even went onto the 8-meter Gemini North and Gemini South telescopes. Each one of these facilities basically copied this and built their own speckle camera. So we've actually done the same thing. This is what a speckle imaging sequence looks like. You basically run at video rates with this highly magnified sampling. So in this case, that was about, it's probably sped up a bit and a subset, but we do 1,000 frames at a time with 40 millisecond sampling. And the upshot there is that the atmospheric turbulence does not go away, but it gets frozen out. You can actually make it at least not smear itself out. If you trip the shutter and you took a 5-second exposure, then again, you're going to be limited to 1 arc-second resolution on the sky because everything kind of gets mushed on top of itself. But if you are short enough, if you're basically on the order of an atmospheric coherence time, this is kind of the characteristic time of the turbulent, boiling atmosphere. If you have if you're working inside of a coherence time, it's still there, but it's frozen out from frame to frame. And what you can do is then mathematically process that. So again, here's another example of what this looks like when you have the individual speckle frames. Each speckle is basically over the face of your big mirror of a 4.3 meter mirror. The atmosphere appears completely clear out to space over a seeing cell, a little clump of atmosphere that's on the order of about 10 centimeters, maybe 20 centimeters in size. And you have a whole bunch of these spread over a 4.3 meter aperture. And each one of those tunnels to space gives you a speckle, gives you a clear spot. And the speckles all kind of get distributed around because those channels out to space are from frame to frame changing. They're frozen out since you're working so fast, but from one frame to the next, they kind of change in size and so forth because the atmosphere is moving in front of you. So you can deconvolve that with a mathematical technique called a Fourier transform. You can basically analyze this speckle pattern for repeating patterns. And if your source itself happens to be a repeating pattern, namely if you have a bright star and you're looking to see if it has a companion star, as you Fourier transform these images and then stack the Fourier transforms, you can actually get to a place where you can rebuild the image at the diffraction limit. This process basically makes the turbulence of the atmosphere go away. And so suddenly we're no longer limited to 1 milli-arc-second resolution. You're limited to the diffraction limit of the telescope, which is about 40 milli-arc-seconds. This reconstruction right here is, I think the separation here between the primary and then this newly detected secondary star is on the order of about 300 milli-arc-seconds. And you could drive a truck between these two things. So we can really get down to much closer separations and still peel closely separated stars apart. So we're using that right now to survey all the nearby M dwarfs. We have this survey called the POKÉMON survey, which is a bit of a tortured acronym that sadly I was the one who came up with that. But we've actually completed the initial reconnaissance where we've been able to look at pretty much every M dwarf star, every low mass star in the immediate neighborhood of the sun. And yeah, this has been about 1,200 targets. So we devoted about 30 nights of time to that from the 4.3 meter telescope here. So we decided to rebuild the camera and do some interesting things. We have the visible side, which is basically like what we've been doing already with this DSSI camera. We did something clever where the light that doesn't go into the speckle imaging, the leftover visible light, we actually push that into a wavefront sensor. And you can basically match up the wavefront sensor with the visible light data and use that to improve your mathematical deconstruction of the speckles that you're getting. And then for good measure, we even put a little filter in that peels off the near infrared channel as well. And we have some near infrared cameras that's making use of that light too. I mean, the whole point is, a 4.3 meter telescope is not cheap, and every photon that it collects off the sky, you should do something with it. And so we tried to be very, very industrious in how we did that. So in fact, here how it lays out. This is a bit of a mess, but the whole box is only about 2 feet on a side. It's very nice. And we built this up pretty much in the beginning of the pandemic times. We got that all put together. And it's all commercial off-the-shelf optics, stuff that you can buy from vendors like Thor Labs or Newport or Edmund Scientific, and just bolts into place. Nothing terribly custom here. And for initial testing, we have these nice 1 meter telescopes that aren't joined into NPOI yet. And so we've had a chance to use those in single telescope mode as a engineering host for this while we tested this out. So the light comes out, bounces over here, you have the visible light imaging, part of it goes over here for the wavefront sensing, and then everything happening over here is this near infrared bit as well. And having demonstrated that at the 1 meter, we've now gotten to first light in the middle of this last summer. You can see the imaging channels happening over here on this one EMCCD, and the wavefront sensor is all these spots over here. This is all being sampled at 40 millisecond frame rates. And we demonstrated it on the 1 meter and then quickly got over onto the 4.3 meter after retiring a lot of risk there and doing a lot of debugging. And here you can see this speckle camera hanging off one of the 4 ports of the instrument cube of the 4.3 meter. And we got to first light on that in July. So that's been very nice. And so just today, we bolted this thing back on to the telescope. I made use of the port, and we're going to be using that tonight to look at a few things. What's going to be ahead is making full use of the data stream. We have this imaging data that's now been taken in a complete lockstep with the wavefront data because the EMCCDs are synchronously triggered. This is a very nice timing board that Mike Collins made for the project. He's been working on Quizy with me for some time. And I think he's a member of your EVAC community as well. And that's going to let us take the speckle data and match it up with the wavefront data, and then try and get to better image reconstructions with that. This hasn't been done in the civilian world, but my colleagues who work at the Air Force Station in Maui tell me that this is a very useful thing to do. So I'm excited to see what kind of results we get out of that. Another thing that I actually did manage to pull off also over the past year, which was kind of fun, is in addition to these ground-based things, one of the things that has been an interest of mine is to someday take a interferometer, take a telescope that's made of small telescopes to make a big telescope, and put one of those in space. And so I've been working with a company called Redwire to do that. Let me show you what, give you the straight up look at what this looks like. You basically have this spacecraft that would have outboard optics, and so this is like a telescope, and on the other side is about a telescope. The idea is you can fly a small spacecraft and it will make itself into a big spacecraft by building itself. So what you have here in each bay is a 3D printer that will print this boom and make this arm that holds your outboard optic here, and then you have a second one that prints this boom over here. Both of these outboard mirror units take light and reflect it to this middle slice of the spacecraft where the beams get put back together and you get your interference and you synthesize your larger telescope. This sounds pretty far out there, pretty fantastical, but when you realize that Redwire and their subsidiary Made in Space is the company I've started with, but they've been subsumed into Redwire, and so that's the main company to keep your eye on now. Redwire and the Forerunner made in space, they've actually had a number of these units flying on the space station. So they've actually gotten quite a long ways up the learning curve on how you do 3D printing in a zero-G environment. They've actually been selected for a standalone flight mission called Archinaut that is going to 3D print the boom structure to support the solar panels for the spacecraft. And so the aim there is to get to a much, much larger solar array that then you could package with some kind of, spring-loaded deployable or some kind of origami fold-out. That's kind of the typical approach right now. They're aiming to beat that by about a factor of quite a few, I think up to 10. And so this technology goes into making those booms. And then the other piece of it is the interferometry. And so I've been working with them. We've had some seed money from NASA, and I came up with a design on how you could feed a beam in, this green beam, and then another beam in, this red beam. This is basically, like I was saying, the middle slice of that spacecraft. And then you send it through a little movable optic right here that can move back and forth. And this accounts for differences in path length out to each arm, because the booms, they're not entirely rigid. They do flop around a little bit. By so doing, you have to accommodate for a little bit of path length difference. And you have to get the alignment and the path length through here good to about 10 nanometers. This is the usual sort of tolerance that is involved with interferometry. And then once done, the beam comes out of the delay line, and you have these optics here that peel it apart and put it into a beam combiner, and you image it with a little camera right here. So we came up with this basically a lab demo, and it was pandemic time, so this was not built up at our optical shop on Mars Hill. This was built in my kids' playroom on a plastic picnic table. So I take this as proof of concept that if it can work on a very dirty environment, on a very floppy structure like this, that will probably have a good chance of making it work on a pretty dynamic environment in space. And so this is where I was at in April, trying to get everything put together. I had somewhat surreptitiously spirited away about 35K worth of optomechanics down to my kids' playroom from Lowell Observatory. A few months later, got to this point where the whole combiner is built up on kind of the right-hand 2/3 of this image. The left-hand third, this slice over here, is a coherent source. You basically have to very accurately simulate a star and then feed it into the input side and feed it into the input side. And after a bit of work, lo and behold, I was able to actually get the light to interfere. And so basically, as this delay line, this little optomechanical stage right here, gets moved around in position, you can see the micron position markers here. As you move it around and sample the photometry coming off the camera in the back end, the amount of light that it appears to see will fluctuate up and down as you get to interference. And this is a classic example of a fringe pattern that we get with light being interfered. So once done, the whole thing got packed up and shipped out, and it went to Florida, because my partners that I've been working with on this, that have all the 3D printing technology and so forth, they're in Jacksonville. And so it has made its way out there, and they are now integrating this prototype beam combiner now into a setup in their lab, which has the prototype beam printing, and the beams themselves are going to be dynamically bent and twisted around to simulate a spacecraft that's flopping around in space, and then we'll track out these fringes. And so we'll retire a lot of the risk that's associated with trying to fly something like this by demonstrating this in the lab. Funny story about this, we shipped this crate out there, and there were all these delays. The crate got lost by the company for 2 weeks. It was supposed to make it out there in a 1-week shipment. So 2 weeks go by, they find the crate finally, and they give the crate, they finally put the crate on a truck, and they get it to Jacksonville, and they pull it off the loading dock at Maiden Space, and Maiden Space opens it up, and it is a car transmission. It is a giant car transmission. It has nothing to do with the crates I sent. And so the running joke is that I succeeded in sending the first transmission from the spacecraft to Maiden Space. But after about another week, they found it, and it managed to get delivered correctly and intact to Maiden Space. It had been placed in the corner of a warehouse somewhere and forgotten about, apparently. So kind of a good resolution, but a little bit nail biting there for a bit when it was on its way out there. I want to finish up with talking about what we've been doing as far as the public programs goes. We have been with the observatory. I mean, we've had a long-standing tradition up on the Hill and a long-standing practice up on the Hill of having a very vigorous bit of research programs like I've been talking about, but also a very, very enthusiastic public program where we don't just try and do astronomy and run telescopes and take data out the sky, but we try to disseminate that information and talk about it. And this has been hard in the COVID times, and we've had a big shift to a lot of online work. Been doing a lot of talks like this, which is a lot of fun. But even in the face of that, we've been working towards having, again, a on-campus presence for that. Part of that actually was kicked off before the onset of our little friend COVID-19, which was the Giovanni Open Deck Observatory. So this was really seen as phase 0 of a really major expansion up on Mars Hill of our public program. And this is a rollaway building with a lift-up roof and 6 large telescopes here, and a nice little plaza. This was really kind of our dipping our toes in the water of having a much more modern, up-to-date experience for the visitors that come up to Mars Hill. And this is more than just a CAD rendering. We've actually gone and built it. And so this is what it looks like. And we have the pop-up roof here. This rolls away. We have telescopes that range in size from some smaller refractors to this 31-inch Dob here. We got a couple of plane waves here, a 14 and a 17-inch plane wave. And it's a really outstanding experience. And so it's been kind of a shame that it's been basically idle for a year, but we've been ever so easily, slightly easing into opening up the public program on a kind of a reservation basis so far. We have a pretty sober and conservative approach to how we've been approaching the whole COVID thing, and basically really trying to tie our closing and our reopening to pretty specifically defined public health metrics and statistics. We were actually one of the first institutions up in Flagstaff to close, and I think that our assertiveness in that regard was also taken as pretty vigorous leadership for the rest of the community, which followed in suit to try and tamp down on this thing. And so we're now trying to take advantage of the fact that the numbers are finally falling and the vaccines are finally getting set in. And so we're going to be reopening gradually over the next few months. And the Giovanni Open Deck Observatory is really a treat. So I encourage everybody to come up the hill and come see us. This is really only the first phase, though. We're going to now build on that, and the real meat on the bone here is something that is our new Astronomy Discovery Center. So we do have a visitor center up on Mars Hill, the Steel Visitor Center that was built in '95. It was built for on the order of about 65,000 people a year. And we currently are getting on the order of about 110 in a normal year. And so we really want to, for starters, accommodate that, but then even build on that. And so this is going to be sized at something twice that, on the order of $250,000 a year. That's about the same sort of visitorship that Meteor Crater just down the road from us gets. And so this seems like a very reasonable number. It also, I think, speaks to our desire to not be a add-on event for people coming to Flag to say go to the Grand Canyon or whatnot. We want to be the reason people come to Flagstaff and be a real destination element of the city. There's a lot of thought that's going into this in how we're designing this with regards to the exhibits and the layout. It's going to be a very nice setup. We're going to have the Universe Theater, which will be a experience for people to be able to see things. We will also have on the roof, we're going to have a rooftop open sky planetarium. So rather than having kind of a traditional planetarium, we have the theater, but then, you know, why have a planetarium when you're in Flagstaff? The skies are so beautiful and typically clear most of the time. The overall building will look like this. You can see this rooftop open sky planetarium here. You know, this will it will also all feed into the campus experience with the Godo and other telescopes that we have on site, you know, the historic Clark telescope. These are all going to be elements of a pretty extensive visitor experience that is going to be a lot of fun. And we're looking forward to building this up. We've gotten the naming support for this. The Marley Foundation has really stepped up to this, and we're still completing the fundraising for this, but we were really, I think, over the hump on getting a lot of this funded. And so we're going to be breaking ground on this, I think, in the next 18 or 24 months or so. And so with that, I'm going to open it up for questions. And see, you know, I've given a wide palette of things that have been going on up at the observatory the past year, but I'll be happy to try and answer anything you might want to ask about.
Oh, thanks, Gerard. That
Sure.
was, now I want to move to Flagstaff tomorrow.
More the merrier.
Yeah. Let's see, in the Q&A, we have a couple questions for you. Bill Peters asks if you viewed the surface field dimming of Betelgeuse last year.
So we did not. We were kind of keen to do that, but we were actually offline for most of that. We had some things that were undergoing maintenance, and so we actually didn't have an actual observing capability at that time, which is too bad, because that, you know, with the interferometer we should have been able to measure if there was any kind of size deviations in that star, or if there was any kind of inhomogeneities in the surface. This is the sort of thing that's been done before with this kind of instrument. So yeah, so it just didn't present itself.
Let's see.
Yeah.
So okay, and I've got Tom Plakas. Would you like to ask your question live?
Yeah, I'm not sure. Can you hear this okay?
Yeah.
Oh, good. All right. Yeah.
Hi,
So
Tom.
I was just going to ask how long those booms are, the self printing booms on the Optimaster. Is that known yet? Is that determined? What's the aperture?
So the current Strawman design is on the order of 10 meters per boom, so a total of 20 meters. We will. That's not anywhere near the 400 meter class size of the NPOI, but we make up for it a little bit in the sense that we don't pay as much of a penalty in working at shorter wavelengths of light. As you go to shorter wavelengths for a given aperture size, the boom lengths, you get more resolution. So we our bogey for that is working down to 0.3 or even 0.25 microns. And that should give us some pretty substantial resolution. It's pretty comparable to a ground-based facility at that point. But that is a bit of a, turn the dial and figure out what the right number is based on the scope of the mission. We're trying to preserve a possibility of flying something as stripped down as possible, which in NASA speak means, like a $70 million spacecraft. But you know, we've had interest and potentially could size this up with longer booms and larger collectors at the tips of the booms, where you know you would fit into more of a NASA MidX class mission, which is like $290 million. And so then you're talking about maybe we go up to 50-meter booms. It's yeah. So a lot of that stuff we're basically exploring all the implications of that, and you know, what are the boom dynamics? What are the implications for guidance and control? What are the implications for moment of inertia and all these kinds of things you figure out? Yeah, it's fun and exciting stuff because it's a neat idea. It's an interferometer in space is something that the astrophysical community keeps on kind of whinging about and saying, yeah, we'd really like one, and nobody's ever flown one as far as a long baseline interferometer. And my distinct sense, somewhat biased, of course, is that once the community gets one of these and sees the power of it in terms of getting to milli-arcsecond class spatial resolution and milli-arcsecond class imaging, they'll soon want a whole bunch more, because there's a ton of astrophysical phenomena that's outside of our reach right now, because the limiting spatial resolution is not 1 milli-arcsecond, it's closer to like 25 or 30 milli-arcseconds with Hubble, and James Webb is not going to improve on that much because it has a bigger aperture, but it operates at longer wavelengths, and so it's not going to get a whole lot more spatial resolution.
Okay, question from Tony. Would you like to ask yours live?
Yes. So you showed a demonstration of what the 4-meter telescope could do. I was just curious, what's the magnitude limit of trying to resolve, closely spaced stars?
So this, for me, is where it's a lot of fun. I've been working with long baseline interferometry for most of my career, and we're talking single-digit magnitude limits on most of these things from the ground, just because of how the Earth's atmosphere behaves. With Speckle, we get down to, on the Lowell Discovery Telescope, we get down to about 15.5. And so it's just a bounty of flux for me as far as being able to look at things. And this has really been a game changer for some of these science programs I'm working on, in terms of, I could do a volume limited survey of the M dwarfs, which are very faint because they just don't give off a lot of light. And, I would never have been possible to do that kind of stuff with long baseline interferometry. So yeah, so that's been great.
Okay, let's see. Rick Scott has a question, but doesn't have his microphone. The amateur astronomers commonly use high-speed video for planetary photography. Would it be possible for them to do speckle interferometry for stellar photography? So this kind of thing can be used in a pretty analogous way. The key difference is where you really dive into the guts of Speckle is when you have a largish aperture such that you have many seeing cells distributed over the face of the mirror. And so you have to have an aperture that's, on the order of a seeing cell size, so 10 or 20 centimeters in size or more, to really get a lot of speckles. That being said, if you do high-speed work with a smaller aperture, it does mean that, that at that point, something simple like tip tilt correction is going to buy you a lot from frame to frame. And so, so the high-speed stuff is very interesting. It's becoming increasingly accessible to large segments of the market because of the advent of the CMOS detectors. They're substantially faster than the CCD detectors with much higher frame rates. There are interesting challenges in calibrating those things, but yeah, it makes it so that this kind of thing is much more possible
at reasonable prices.
Okay, one from Tom Curry, also without a mic. When you're splitting the beam for different frequencies of light, do you lose resolution or intensity in the other frequencies?
So when you take broadband light and you have a beam from one telescope and a beam from another telescope, and you blend them together to get an interference pattern. If you keep it broadband, if you don't spectrally disperse it, that does affect the strength of the signal, especially if you are away from a zero path condition. If you're away from equal distance from telescope A and equal distance from telescope B, it's actually very useful to zero in on if you're actually at the true zero position between of equal distance between the two arms of the interferometer to use broadband light. Yeah, it's a help and it's a liability at the same time, because then it means that if you're not right at the equal path length condition, it's hard to tell wherever you are. So we play games with how much dispersion we use to accommodate that.
Okay. I'll squeeze in a question of my own.
Uh-huh.
Is the AO software come in a CAN package, or do you have to tune it yourself?
So right now, we have a kind of a lab bench set up on 2 of our 1 meter telescopes, which is literally a pile of spare parts from NRL. And that's spare hardware parts. And so I've had a couple of undergrad students cobbling together the software, and that's also kind of Frankenstein effect. We are in the process of setting up some funding that's been assigned to us, where I'm going to turn around and cut a check and get a commercial system provided to us from a vendor, where that will be all canned. And but the neat thing about that is there appears to be more and more vendors out there with better and better software to match the fact that the hardware is pretty good, and they're not soaking you for it. And so there looks to be, like, reasonable kits you could get for, let's say, a 40 or a 50 actuator system in the neighborhood of 60 to 75K, which is a lot of money, but is about a factor of 5 to 10 cheaper than what it used to be. And so we have some special requirements, so that'll probably drive the price on us upwards from that a ways. But it's definitely a lot of this technology is becoming a bit more affordable, which is good.
That definitely sounds good. Okay, question from Helen. Helen, would you like to ask your question? Do you unmute yourself? There we go.
Haven't tested the microphone, so I don't know how I'm coming through, but
That's good.
we were out there in 2019. We visited the observatory, and I wondered where the new buildings that you just showed were in relation to the ones that were there before.
So the GOTO is the big new thing that we have, and if you remember where the water tanks were, it's basically the water tanks were on the hill just next to the Slifer building, the building with the dome in front, and we took those out. We put in a new water tank elsewhere, and then one water tank we tore down, another one we gave away, which is kind of a neat trick. And that's where we built the GOTO, because it was the high spot on the hill, and presented the best views of the sky. And so that's been the main new thing on that time frame. The other more recent building is the collection center, and that would have been there in 2019. So the GOTO is the main thing so far.
Thank you.
Let's see. I see a question here from Woody Sims about where did I get my optical bench?
Are you there, Woody? Or okay, go ahead. Where did you get
Sure.
the optical bench?
So I went to two vendors. I assume you're asking about the bench. I showed a couple of benches during this talk, but so the bench for the adaptive optics on the 1 meter, there's a company called Vere, V-E-R-E, that is very good. And they will build you any bench you want out of any material you want if you're willing to wait for it. And unfortunately, Vere's a little slow with things. And so some of the subsequent benches I bought from a company called Base Lab Tools. And yeah, the Vere bench showed up after about 6 or 7 months. And Base Lab, I gave a call, and they're very apologetic. They said they would not be able to get me my bench for 3 days, and would that be okay? And so it was pretty amazing. Yeah, so Vere's the better quality bench, but you got to wait for it. So yeah, you get what you pay for, and you get what you wait for. So
That do it, Woody? I was slow on unmuting you, so.
Yeah, which one is the black optical bench that had all the holes drilled in it? Is that the Base Lab Tools one?
I think yeah, I think that was a Base Lab Tools one. They all tend to have the face plate with the 1/4 holes all across them. Actually, the one I got built for the spacecraft demo experiment was not 1/4 holes. Those were all M6. That was metric. So it's a mess mixing metric and SAE. So.
And did you by chance 3D print a lot of the parts that you attached to those holes on the optical bench?
So ironically, not for the demonstration for the 3D space printer, but for the Speckle camera, we printed a few parts that were in particularly tight spots to hold a mirror in a particular way. We printed a few of those, and that worked okay. I mean, we didn't even get that fancy with it in terms of we just used I think ABS plastic or PLA and mounted the stuff in that. You know, for a price, you can print, send a file away and they'll print stuff for you in metal. And we held that as a option in reserve, but never exercised it because the stuff in plastic actually was fine.
Great, thank you.
All right. And we've got David Goshal, sorry. Go ahead, ask your question. You're on, David.
Oh, okay. Can you hear me?
Yep.
Okay. The spacecraft with the 2 arms, presumably it's going to be launched from one of the main launch sites. Do you know at this point where in space they would actually locate that unit?
We have our inclinations on that, and it's someplace high because one of the problems with low Earth orbit is getting a lot of shadowing and in and out of eclipse. That's going to create a lot of thermal inertia, thermal differentials in places. Even a sun-sync polar orbit in low Earth orbit has an eclipse season. And so most of the time you're in direct sunlight, but not all the time, actually. You get some times of the year where you're going to get hit by some shadowing. So that's kind of, it's a disturbance we don't want to deal with. And so the desire is at the very least something like geosync, but the most likely spot that we would really like to have would either be L2, where they're going to send James Webb and have sent a lot of other observatories like Gaia and Herschel and so forth. But a really ideal spot is L1. And so the thinking there is L1 is the Lagrange point where you can park a spacecraft between the Earth and the Sun, but it's the one on the inside of the Earth and the Sun rather than L2, which is on the outside. With L2, you line up, it's Sun, Earth, L2, and L1 is kind of interior that with Sun, L1, Earth. And the reason for that is that you can look back in the vicinity of the Earth. And one of the things that we really want to do with this is with about a 20-meter baseline, you actually have a real sweet spot in resolution for looking at near-Earth asteroids. If you have near-Earth asteroids with a characteristic size of 10 meters in size or even 100 meters in size or smaller than that, you could actually measure their sizes. The really interesting thing is there appears to be quite a few of them that are binary. And if you map the orbits, that gives you the mass. And the mass, along with sizes, which you would also get from this, you can basically infer composition. And this has a lot of implications for Earth defense. If you're going to have a body that's coming towards you and you want to do something about it, it helps to know if it's a solid rock or if it's a rubble pile. And this will help do a survey of these sort of bodies that will give you a sense of what the typical disposition is for these things. And so this is something that is very practical, actually.
Yeah, sounds interesting. Josh, you're on. You can go ahead and unmute yourself. His question was about if you had any thoughts about the 10,000-year storm on Jupiter.
I don't know a lot about that. I mean, as far as the Great Red Spot or some of the other ones, yeah, I don't know a lot about that kind of stuff.
Okay. Let's see. We'll move on to Jim. Go ahead, Jim. You're on.
Great presentation. I wondered if you could compare the thoughts of your interferometer measurements with the resolution of the projected resolution of the Giant Magellan Telescope.
Yeah, the GMT is, I believe, effective resolution is going to be there about roughly a 25-meter telescope, and so it's yeah, it's going to be in that ballpark. And so for example, the Navy interferometer at its compact configuration typically has separations and therefore an effective size from a resolution standpoint on the order of 10 to 20 meters or more. We frequently run with a setup where we have some of these smaller 12-centimeter siderostats working together, and they present baselines of, I think the shorter ones are like 18 meters, the longer ones are 40 meters. And so for bright things, we can easily get to much greater levels of resolution than something like the GMT, because that's our compact configuration, and we can easily run at 80, 90, 100 meters, and we're working on opening up our stations that are out at 430 meters. Where things like the GMT or the TMT or the ELT beat us handily is the fact that they're not as spread out, but the size mirror that they do have is all mirror, and so they don't have a lot of light falling on dirt like we do, and so they can look at things that are a ton fainter than us, and that's their main science case, is faint, fuzzy, and far away. And we like to focus in on brighter things that typically are nearby. And the point I always make to people is how with bright things, just because you can walk outside and see a star with your own two eyes doesn't mean that we know everything there is to know about. In fact, quite often, those sorts of objects are poorly known for the simple ironic fact that the most advanced instrumentation in the world are on big telescopes, and they not only have faint limits of how faint can you go, but they have bright limits where you can't look at something too bright. So a lot of things that you can see with your eyes have been forgotten about in professional astronomy. And so it's a lot of fun to have things now that look at these things in new ways. And, you know, best example I can come up with on that is, you know, some years ago we looked at Altair and mapped its surface and, you know, found that it's shaped like a beach ball that you've squished in your hands. And associated with that phenomenon, which comes from the fact that the star is spinning so fast that centripetal acceleration is starting to compete with gravitational acceleration, you get all kinds of temperature effects across the surface of the star. And this had not been seen before, even though this was a first magnitude star. And so there's plenty of interesting things to find out about bright stuff out there. So that's why I think these sort of telescopes have a real strong position in astronomy nowadays.
All right, thank you. And we got Chris with a question. Chris, would you like to pose that yourself?
Sure, thanks for a great talk. And
thank you.
The question really was revolved around the satellite-based interferometer. Was pretty intriguing. What about where are we at with the lunar-based one? Because obviously there might be some advantages with no atmosphere, the potential to service it in a stable platform.
So the big thing in my mind with that kind of thing is, to let you hit the nail on the head, is stable platform. We kind of go through a lot of hoops to deal with a kind of a floppy, sloppy satellite platform, and we can make it work, but it definitely changes the equation if you have, you know, a big reaction mass and can basically sit on the surface of the moon. Years ago, when the Constellation project was a going concern, as far as the last time we said we were going to go back to the moon, which has happened many times since Apollo, if people have been keeping an eye on these sorts of things. But yeah, with George W. Bush with Constellation, we were approached for ideas on things like this, particularly in the realm of following the pattern of Apollo, which was the suitcase science. Sure. And so for an interferometer, we came up with an idea of a suitcase and two carry-ons, where we would, you know, have a central combiner that the astronaut would put down, and then you basically put the two carry-ons at some distance apart from that. And, you know, the only thing you're allowed to require of the astronaut is that they push the on button. And, you know, that'd be actually pretty easy to set up to come with. We haven't spent a lot of time on developing that kind of idea further because, you know, despite lots of brave talk at that time, there's been no surface access to the moon. And maybe that'll change soon. It seems like there actually is a lot of momentum in that regard that's being held up even with between the change of the administrations here. And so maybe there will be opportunities like this that'll open up, and that actually is very interesting. I think I certainly am paying attention to it and keeping an eye on that. I think the in-space manufacturing is exciting and transformative on how we just do business in space, period. But I'll take whatever ride I can get to get an interferometer in space if it's going to be either floating out there or sitting on the surface of the moon. So it'll do great science either which way.
Well, not to take up much more time, there's two initiatives coming out called PRISM that are announcements. They're about $50 million demos for 50 kilos. They bring you to the surface, and if you can provide the science demo, they're looking at possibly of 2 of those per year, and that's just starting to happen now.
Oh, interesting. I had not heard of that. I'm going to make a note of that right now. Yeah, there's definitely interesting problems at the surface, most notably dust and that kind of thing, but it also solves a lot of problems as well. So that could potentially be pretty useful. So yeah.
Okay, move on to Brooks. Brooks, would you like to ask your question live? I'm not sure I completely understand the question about can a system like this look at star distributions or limited to a single point source?
So it's much easier to look at point sources. Let me actually, so the example given by the questioner here is, can you look at star distributions? And the short answer is yes, is that for those sorts of things, it's, you can peel apart the sources with the signal coming out of the back end. An even more complicated example is the sort of thing I get approached by customers sometimes, which is what happens if you're in, let's say, geosynchronous orbit and you're looking down. Can you make images from stuff on the ground, which is a much more complicated scene. That's hard. That requires quite a bit of thought on how you put the beams back together and how you rebuild the image from a distributed telescope. It's tricky to do with a conventional telescope, much less something that has this kind of architecture, which requires a bit of gymnastics to put the pictures back together.
Can you hear me
So,
now?
oh, yes.
My question on that was really kind of pointed more at looking at the globular clusters, because I know they're looking to track stars to try to determine if there's black holes in the centers of some of these. And it seems like they would be in the brightness limit that you guys can look at, but when you got 10,000 stars packed into a pile, can you separate all those signals?
Yeah, and usually that traces back to questions about how well is your pointing accuracy of the overall system, and that can actually be very tricky to get right. It's a lot easier if you're looking at an isolated star and you're trying to measure its size or see spots on the surface of the star, but the object itself is pretty close to being a point-like source. And so when you have a very complicated scene like you've just described, that can be hard to do. It's I think the sort of thing that we'll solve, but yeah, you got to kind of mind the math on all that.
Not impossible, but not today.
That's right.
Thank you.
All right, thanks, Brooks. Okay, I saved a couple questions for the end.
Yeah.
One is, can any of the outreach telescopes auto guide, and do you have any reservations for people to stay a little bit later?
I'm not sure what the public program is doing with that, actually, because there's certainly been talk of that for making use of these very nice telescopes for groups exactly like that. I think there is a clear recognition that there is an appetite for that and a market for that, but I'm not sure how that has developed. I think a bit of that sort of thinking has been a little bit tabled because of the whole COVID thing, but I think the idea is we're certainly going to circle back to that. So I would say keep an eye out for that. I don't know the details on the guiding though, the technical capabilities there. I do know like I mentioned, two of them are plane waves, and all my stuff is plane wave, and that stuff doesn't need guiding. It's great. So
takes care of that.
Yeah.
And I was just wondering if I got a couple of the numbers right. Were you saying the atmospheric coherence time was about 40 milliseconds?
So the actual number for that in the visible is actually quite a bit shorter than 40. It's closer to 5 to 10 milliseconds. And so we cheat a little bit with the speckle imaging by going a few factors beyond that. So there's actually some smearing in our signal, but then you get more light. So it's a bit of a trade-off.
Okay. And I was just wondering if I understood it correctly earlier. Were you going to do speckle imaging in space?
Not speckle imaging. It'll be the idea with the thing that we've been demoing is true long baseline interferometry. Yeah.
Okay. Yeah, that made more sense.
I think speckle has some interesting options and opportunities in space, because the thing about space observatories, and I don't think this has been really fully appreciated by people that build and operate such things, is that to a certain degree, you don't need to build everything to, you know, 100th of a wave tolerance. That you could actually potentially be a bit more sloppy about things, but as long as it's static and as long as it's, you know, an unchanging error, you can, with enough signal and noise, you can calibrate a lot of that stuff out. And so this was one of the things that originally got me involved with working with Made in Space. Is I was talking with them about printing the aperture, print the mirror, and you know, recognizing that it's never going to be a great mirror. It's going to be a terrible mirror, but it's the same terrible mirror the whole time. The distortions in the wavefront are going to be static, and that you can calibrate that out. And if you print a mirror, it doesn't have to survive launch. It doesn't have to fit in a payload shroud, and it can be really, really thin. And you could easily conceive of printing a mirror that is 20, 30 meters in size.
Wow.
And suddenly that signal to noise that you need to calibrate out the wavefront distortions, you've got a lot of signal to noise. So I still want to do that. But the interferometry is more in my wheelhouse, and also I think a clear line from start to finish to do at least now. And it opens the door to more concepts and things with in-space manufacturing. So that's, I think that's, you know, it's the it's going to be the gateway drug.
Okay. All right. I don't have any more questions, and I don't see any more on the board. So
Okay.
Thank you very much for a nice talk.
Yeah.
See how much
My
interest you
pleasure.
had. Yeah. Everyone's excited.
Excellent.
Go
Yes,
ahead,
I have to go off and go observing now. So.
Okay. Use that stuff.
Yep.
All righty. I'll turn it over to Gordon to close the meeting out.
All right. Well, thank you, Gerard.
Yeah.
For a very interesting and educational presentation about things happening in our own state. And we can tell how popular it is by the number of questions that we had directed to you. So thank you for that. Thank you. And Bruce, sure. Thank you for your presentation, where we learned that in space you have to slow down to catch up. And again, lots of people, lots of comments about that was a good presentation. So thank you very much. So guys, we come to an end of another monthly meeting with 2 great presentations. And join us again next month, March 19th, where we'll have a main presentation about the far side of the moon, radio astronomy. So that sounds interesting. So guys, I think that will do it for this time around. I will give the usual countdown and we'll close this meeting out. All right. Any other comments? All right. We got 3, 2, 1. Bye, y'all.